Hello everyone, this is a recording of my final project for Duke University course Machine Learning Foundation for Product Managers. So the problem statement that we have here is we have to build a ML model which can predict the electrical energy output of a combined cycle power station which uses combination of gas turbine, steam turbine and heat recovery steam generator to generate power. Here we have bunch of features, variables using which we have to build this model. So the independent variables that we have is temperature, ambience pressure, relative humidity, exhaust vacuum, and the variable which we have to predict is net hourly electrical power output. The data can be downloaded from this link. It's a CSV file. Data is in a tabular format. It's a well-structured data. So to build this model, this is the flow that we're going to follow. I mean, the flow which I have followed. A modeling approach is the part where we'll try to understand the data which has been given to us and the features, and we perform the initial level of feature analysis and decide which model to select. And as part of this stage, we'll also identify the metrics that we are going to use in order to evaluate the model. As part of model building, we will be uh, using the features which we have identified as part of our analysis and build the model using the mix of different features. And followed by that, we will evaluate the model which we have built as part of this process, and see the output, how the output metrics look like, and based on that we will interpret the outcome of this modeling. So as part of a loading and pre-processing process, as I said, the data is given in a CSV format. We will load the data, and I have used Python libraries in order to build this model. So using pandas, we are loading the data from CSV, and here is at a high level the five features which are available in that CSV file. I've verified that there are no missing values, so data is complete and clean, and we don't have anything missing, and all the values are the numeric decimal values. So as you can see here on the left, that data is not in the normalized form. So as part of this loading and pre-processing process, I have normalized the data so that our model will perform well. So as part of feature analysis, I have done a correlation matrix and plotted that on a heat map, and we can see here the correlation between the different features which are there. And as a practice, we'll be selecting the feature where the correlation values are greater than zero point 0.5, which shows the relationship between those features. So we can see here clearly from the graph on left that ATV and AP are strongly correlated. So we will be considering those and will further perform the analysis. And on the right hand side, you can see I have further taken those three features and have done a correlation again. And as part of this, what we will be considering is, we will, from these independent variable, we will be uh, not using the features which are highly correlated to each other out of those three features which we have identified as part of the step on the left. And based on that, we will be further selecting the feature, and we'll be making a different combination in order to train the model. As part of this, I have selected three models: linear regression, decision tree, and random forest. And as I talked about in my previous slide, these are the four combinations that I have used in order to build and train the model. Model 1, where I am only considering one variable. Uh, in the second model, uh, another variable, that is V. Third is a combination of V and AP. And fourth is combination of these three variables. So just want to highlight, as we can see in the previous slide, I have mentioned the ones out of these three selected variables, we will not select those two variables which are highly correlated. That's why you can see here in model 3 I have selected V and AP to predict the value of P, and I have not considered AP and AT. As you can see, AP and AT and V and AT, they are highly correlated, so I've excluded that. So as part of model building strategy, I have split the data into 80-20, where the 80% I have used for training set and 20% for the validation set. For model evaluation, I have used RSME, MAE, and R square to evaluate the performance of those four models. And you can see here the output, or the output of different matrices that I have used. As you can see here in model 1, where I have used 80 as the only input feature, the three model performance we can see here: a linear regression, decision tree, and random forest. We can clearly see here that linear regression is the winner in model 1. In model 2, where we have used only one single feature, that is feature V, again the linear regression has performed very well. In model 3, when we have considered two different features, that is V and AT, we can see a random forest has performed very well. The R square value is 98%, and MAE and RSME is pretty much good compared to what do we see in linear regression and decision tree. And when we have considered all these three features, that is V, AT, and AP, we can clearly see again, and the random forest has performed very well, where the R square is 98%, and MAE and RSME are comparatively better than RSME, MAE in decision tree and linear regression. So we can clearly see that regression tree, the random forest is the clear winner, which we will use to build the model as our final model. So based on the model 4 output, we can clearly see that our random forest is the go-to model, and the feature that we'll be selecting for this model is VAT and AP, so that we can predict the value of target variable, that is PE. So before using the final model as a good practice, uh, the split which we created in the beginning, that is 80-20, what we'll be doing is we'll retrain the model with 100% amount of data to get a better results. Thank you everyone.